Let's get to the session. Let's get to know how thermal management works in computers. In simple terms, how heat management works in computers. From microscopic transistors to massive air clusters. Let's first get to know how actually heat is generated. Like we know that when for running the computers, we require electricity, right? So this electric current is required as the food for the computer to run any sort of computations. And the subsidiary product which we receive, which is the excess per se, is the wasted energy which is converted into heat. So the residue of what is not used by the system for the computing is released in the form of heat. Every computation requires electricity to flow through transistors. Modern CPUs contains billions of transistors, switching billions of times every second. No processor is 100% efficient. It means that not not even a single CPU, not at the current time, is not advanced enough to use 100% of electricity without giving out any sort of residue, which is heat within this situation. So due to the electric resistance, it turns the wasted energy into heat. Core insight: computation is fundamentally an act of generating heat. The escalation of unchecked heat. Let's get to know how the bar is like. What are the different stages as they go on based on the severity because of the heat generation if it is not controlled properly. So the first stage is the reduced performance, which is called as thermal throttling. The second stage is the system instability and visual artifacts. It means that the operating system gets unstable, which causes a lot of issues, and the visual aspects, like what you see on the screen, gets hurdled, like the screen getting blank or the screen is having fluctuations, those kind of situations. And the third is the unexpected emergency shutdowns. The system suddenly stops, the crashing of laptops, the operating system crashes. So these type of situations are considered as stage three. And when it comes to the stage four, it results in the permanent hardware degradation. These stages are accordingly how high the temperature is. Like as the temperature increases, the effect on the system, first the software and next to the hardware, increases. The infrared blueprint, component level thermal analysis. Let's get to know what each and I mean how much heat is generated by each and every component as well as different types of computers. VRMs, they are power converters which generate secondary heat. CPU is the core heat source because CPU is the one which is running almost each and every time, right? Because it is the central processing unit which takes care of almost all the executions. And next is NV SSDs, the memory units. They also generate heat. The one which generates the most heat, which can even exceed 450 wattage, is the GPU, graph processing unit. Next, let's get to know device level analysis. Laptops usually generate the exact measurement of heat a cooling system must physically dissipate. Let's get to know about it. So, what it actually means is that how much heat is generated by each and every type of device. Laptops generate 15 watts to 45 wattage approximately. Desktops generate 65 watts to 250 watts approximately. Servers, on a minimum, they generate 250 watts, and based on the scale of the server, based on the number of units, it can go way above 400 watts. The anatomy of heat transfer. Let's get to know from the first point, which is the CPU die. The tiny silicon chip where massive power density originates. Because as we know, CPU is the main processing unit within the laptop, which is always running. Integrated heat spreader. Metal cap spreading concentrated heat across a wider surface area. So it is going to widen the surface, widen the range of the heat so that it dissipates. Thermal paste, the crucial bridge layer. Um, Thermal paste is like a material which is going to make sure there's a proper conductivity. Like uh, even if the surface seems to be flat, the metal surface of the components of the hardware components is not actually exactly flat. It's not completely smooth. So thermal paste is required so that there is a proper conductivity to dissipate the heat. Integrated heat spreader. Metal cap spreading concentrated heat across a wider surface area. So we are going to have another of it. We are going to have it on the two sides. CPU die, the tiny silicon chip where massive power density originates. And again, so this is the anatomy of heat transfer. And at the above, we are going to have the fan. So like we are going to have multiple layers, like we are going to have a thermal paste, we are going to have two layers of CPU dies and two layers of integrated heat spreaders. And we are going to have a fan which is going to push ambient air across the fence to carry heat away via convection. And are going to have the heat sink, which conducts heat upward into dozens of fins to maximize the surface area. So this is the anatomy of heat transfer when it comes to a CPU. The micro gap metaphor. To the naked eye, a CPU and heat sink appear perfectly flat, but they're not completely flat. Uh, when we go into a more smaller level, under microscopic level, the metal surfaces are jagged and uneven. These microscopic gaps trap air, which is highly inefficient thermal conductor. As you know, air is a insulator. Insulator in the sense which is not going to conduct any heat. So the solution which we are going to use for this is the thermal paste. Thermal paste is going to fill these microscopic canyons, displacing insulating air and establishing an unbroken chain of thermal conduction. So this is the reason we require thermal paste. Airflow dynamics, managing the ambient environment. We are going to have two different types of airflow dynamics. One is the positive pressure and the other is the negative pressure. More intake fans than exhaust fans. It creates internal pressure that naturally pushes air out. So it is going to push the air out. Primary benefit prevents dust buildup. Negative pressure. More exhaust fans than intake. Creates a vacuum that forcefully pulls ambient air in. Primary benefit slightly better raw heat extraction. The ultimate goal, a directional wind tunnel that removes accumulated heat instantly. The dynamic power protection loop. So we are going to look at a cycle first, which is the sensors detect heat. Embedded sensors monitor CPU, GPU, and VRMs thousands of times per second. Fans curve, fan curve suggest. Motherboard dynamically ramps up fan speeds to balance cooling and escapades. And the third step is the thermal limits reached. Component hits maximum safe operating temperature. So, for example, 95 degrees Celsius to 105 degrees Celsius. Thermal throttling engages. So, when the heat reaches a threshold, the system deliberately slashes clock speed to drop temperatures. So, it means that it's going to increase, like it is going to go to the max of the clock speed so that it can drop the temperature. But if that isn't enough, then it comes to the emergency shutdown. If the temperature of the device reaches a very high threshold, this is the final hardware defense if throttling fails. For suppose if the throttling doesn't decrease the temperature. The portable balancing act. Zero room for massive copper heatsinks or optimal air flow pathways. This means that based on the size of the device, we wouldn't be able to have massive copper heat sinks, right? Like These are devices which are used for carrying outside like portable laptops. So we wouldn't be able to have any massive heat sinks or optimal for platforms, which require the hardware to be even at a higher scale, even more larger volume per se. So heat, the next point is heat pipes must rapidly transfer concentrated heat laterally away from the keyboard and the user. So as you know, when it comes to a laptop, we are going to have the ducts at the below the laptop on the sides of the laptop so that it wouldn't reach us, not towards us. The engineering reality. You cannot maximize everything. A quiet, cool, high performance laptop with longer battery life violates the laws of physics. Well, as you know, if as the amount of compression increases, the amount of electricity which it would require would increase, and the amount of residue would also increase, thereby increasing the heat. So what it actually means is that we wouldn't be able to have a high performance laptop which wouldn't have any, um, which is going to be cool because it there will always be a situation where it's going to conduct where the heat is generated, right? But yeah, we do have laptops which have higher lifetimes based on the quality of the components, like Mac laptops which give a long-term performance. But along with that, they don't have the raw computational power of Windows laptops. Advanced extraction beyond air cooling. So beyond air cooling systems, we are going to learn about two different types of other components which are helpful for thermal management now. One is vapor chambers. They are flattened heat pipes used in GPUs and high-end smartphones. They spread localized heat horizontally across a massive surface area almost instantly. So as you know, rather than having the heat at a point, it is going to spread all over the device. Next is the all-in-one AIO liquid cooling. A pump pushes cool liquid over the hot CPU die. The hot liquid travels to a massive radiator where fans blow the heat away, replacing the air convection at the CPU source. So this is called as a liquid cooling, where we're going to have a radiator which is going to remove the heat from the liquid, and this cool liquid will be sent again to the CPU. So this will be a cycle which always sends the cool liquid to the components so that they cool down, and where it is going to take the heat, and the heated liquid goes to the radiator to cool off. So it will be a cycle of liquid cooling. The macro scale, AI and data center bottlenecks. Modern AI hardware pushes the absolute physical limits of thermodynamics. A single AI GPU cluster consumes thousands of watts, concentrated in a few square inches of silicon. Traditional air conditioning is vastly insufficient to prevent immediate thermal throttling when thousands of GPUs are stacked together. Cooling is no longer an afterthought. It is the primary engineering challenge of the AI era. As you know, the reason for it is because the hardware which is required for the AI, the GPUs, they do massive processing, which requires massive electricity, which thereby conducts a lot of heat, which thereby releases a lot of heat. So thermal management is at most required. The ultimate evolution, immersion cooling. So the solution which has been found for this situation is immersion cooling, where entire server racks are completely submerged directly into specialized non-conductive dielectric fluid. So what it means is that this liquid doesn't conduct electricity. This liquid conducts, so the heat is dissipated. So when we have large AI clusters, large servers which are doing this processing, these are put in an immersion cooling where which is like a isolated space of cooling liquid, which is a non-conductive dielectric fluid. The benefit: unmatched heat removal capacity. The liquid touches every microscopic device of the hardware, absorbing heat thousands of times more efficiently than ever. The standard for next generation high performance computing and supercomputers. So this is what is used for the processing parts of large servers or large HPCs, high performance computing and supercomputers. The cooling technologies matters. So let's get to know about these three once again in a more differentiated manner. First is the air cooling, second is the liquid cooling, and third is the immersion cooling, which is latest. So let's get to the first one, which where we're going to get to know about the brief overview again, which I have gone through. The mechanism of the air coolant, it is via fans or heat sinks. When it comes to the liquid cooling, as we have got to know, it is like a circulation through to the required components where the liquid cooling system, the liquid passes through them and the heat is absorbed by the cooling system and it goes to the radiator and the radiator is going to dissipate the heat using a fan and this cooled liquid again goes back to the components, per se the processing systems, the processing units. So there is a liquid cooling system and the immersion cooling where the parts are submerged in a dielectric fluid. Maintenance, the air cooling maintenance is low where we just need to remove the dust by using by just removing it manually or using some sort of paste. And for the liquid cooling, there is a problem of pump failure risk where if the pump doesn't work and it doesn't circulate, then the cooling system doesn't work, right? So the pump needs to be replaced in these type of scenarios. And the third would be the immersion cooling, where the specialized, where the maintenance would be even more higher because there needs to be a manual process of removing the liquid, which is not removing the liquid manually and putting it back in. And let's get to know about the primary use cases. The air cooling, which is also we can call it as a legacy cooling system, which is used normally within our daily devices like laptops, smartphones. When it comes to liquid cooling, it is very much used in gaming desktops or gaming laptops. Or when it comes to GPUs, which generate, like within the laptop, it's mainly used for within the GPUs, which is going to produce a lot of heat because of the massive processing. So it's used for like high-end gaming workstations. And next we have the immersion cooling use cases. It is mainly used for servers, AI clusters, and supercomputers, basically high performance computing. The blueprint grocery, let's get to know the total overview once again, like the breakthrough. So the first we have the CPU, which is the engine, which generates massive heat as the inevitable byproduct of computation. Then we have the thermal paste, which is the bridge, which eliminates microscopic air gaps to force efficient heat transfer. Next, we have the heat sink, which absorbs localized heat and expands it across a massive surface area. The fan, which speeds the accumulated heat away from the system entirely. And next is the thermal throttling. Thermal throttling is a situation which occurs when the temperature reaches a threshold and it starts to run the fans to their limits to reduce the temperature. If that doesn't work, then the system crashes because if it reaches a certain even higher threshold and the temperature doesn't drop to save the device, that's what emergency shutdown is required. This is the system's self-preservation instinct to drop performance before destruction.